Okay, folks, well, welcome to lecture number 3, the online-only version of this lecture. Again, I regret that I'm not in class with you guys today. At the present time, I should be making my way through Atlanta Airport, and I'll be back in Mobile in approximately 1.5 hours. So I'll see you in the hallway if all goes as planned. Today's lecture is going to be talking about petroleum, at least the first part of a two-part lecture on petroleum. Today we're going to be talking about generation and migration of petroleum. Now, if you're wondering why we're talking about petroleum in a class that's dealing with geophysics, it's because I'm trying to give you as much of a comprehensive introduction to petroleum geology as possible. Last time we were talking about the physics of seismic waves that geologists have to be a little bit familiar with. It's also important that geologists are familiar with how petroleum forms, how it migrates from point A to point B, and ultimately how it gets concentrated in the rocks. So, as I said, it's an important aspect of petroleum geology, and while it may not be specifically geophysics in nature, since this is the only experience you're going to get in petroleum geology in the undergraduate degree at the University of South Alabama, it's needed to be discussed somewhere, and this is the best place to do it. Now, before we talk about that, let's consider what we did last time. We were talking about refraction and reflection. Not my best lecture, and for those of you that didn't quite follow what I was talking about, which would probably be most of you, I encourage you to look at the online version because I redubbed things and I think it flowed a little bit better. Anyway, last time we met, either in the class or in the online version, we were talking about wavefront mechanics, we were talking about wave propagation, and then we had our first introduction to the way that seismic waves refract, reflect through rocks, and introduced the whole concept of Snell's law. And while we were talking primarily about Snell's law in relationship to optical waves, it's important that you associate those waves as being the same as seismic waves, because all waves share similar properties. We talked initially about how waves are initially transmitted as spherical expanding shells, and after a while what happens is the sphericity of the waves tends to flatten out, giving you what is best described as a plane wave. We talked about how there's a propagation direction as well as different vibration directions within the wave form itself. I introduced you to a little bit of math, but I told you not to worry too much about it because, frankly, we're not going to go into the details of mathematics here. So the two expressions that you see here were ways in which you can model one-dimensional behavior of seismic waves traveling through rock. And then we started getting into some principles that have relevance to both optics and to seismic waves through rocks. We started off with Huygens' principle, which states simply that all points in a wavefront can be regarded as point sources for the production of new spherical waves. And the idea here was that each of these spherical waves, when they come together, start to be describing what is essentially the wavefront for the waves that will propagate through rocks. This has applications, of course, when you're dealing with the way waves will reflect off of other surfaces. Here in this diagram, the surface is shown as an interface between two materials. The first material, the overlying material, has a wave velocity of alpha 1. The second layer beneath the interface has a velocity of a2. That gives rise to a contrast in densities, and that will cause waves to refract and to reflect. Now, this diagram shows you the reflection component. You'll see again the angle of incidence, the angle of reflection. The next diagram here shows you what happens with the refractions, and again you can see the expanding waveform shells that determine where the wavefront is going to be. Then we got into Snell's law, and again this is something that we are particularly interested in when it comes to mineralogy. I tried to explain that to you last time, that Snell's law is one of the vital components of how we resolve subtle differences in very fine-grained minerals like the clay minerals. We'll not have to go into it again here, but while Snell's law does apply to optics, there is basically the version of Snell's law that applies to seismology is called the law of refraction. Okay, now that more or less summarizes what we did last time and finishes our physics of wave dynamics in this course entirely. Today we're going to change things around entirely and start talking about how petroleum forms, migrates through rocks, and more or less accumulates in certain places. For today's lecture, we're going to be talking about petroleum in general. We're going to talk about some subsurface fluids, and then start getting into the whole idea of the migration of petroleum. Now I'm going to give you an advance warning. This material is largely chemical based this time. Worse, it's based upon organic chemistry, which is another of those disciplines that geology students don't particularly enjoy. Actually, not many people enjoy the organic chemistry aspect of things. If you believe the biology students, since so many of them actually were having problems with organic chemistry too, that the biology department introduced a minor very similar to our composite sciences minor, where biology students could elect to not take chemistry but could substitute other courses, including geology courses, for their organic chemistry too. Like our related sciences or composite sciences minor, students that are planning to go to graduate school are encouraged to do the full tilt minors. But they needed to introduce something because of the issues with organic chemistry. Fortunately, our organic chemistry today is not going to be anywhere near as difficult because it's basically petroleum based rather than pharmaceutical or biomedical based. Okay, now I suppose before we start getting into the whole idea of petroleum formation, etc., we should perhaps discuss a little bit of career opportunities in petroleum geology. I'm trying to stress as much as possible the options that will take you into a career in this field. The previous couple lectures, when I was talking about wave dynamics, I was again stressing the idea that if you become a geophysicist with an oil company, you'll be expected to understand the physics behind how waves propagate through rocks. The geophysics profession is quite highly sought after now because it's one of the major techniques of exploring for economic resources like oil and natural gas. But there are other aspects of careers in geology if you're not all that keen on geophysics, and yet you still want to work in petroleum geology. There are other options available for you too. Now, before we discuss those things, it's very important that you realize that you don't work alone when you're a petroleum geologist. What you have to do is work in teams. And the reason for this is that you're talking about a very expensive and technology-focused position. And for the most part, you're going to need teams of people just to handle the amount of data you got to deal with. Okay, so the idea now is that if you are working petroleum, you get hired on, you'll be appointed to either a development team or into some sort of a regional exploration team where you will work in conjunction with other people. The actual positions that you can get, we talked about the idea of a geophysicist, and your job would be, of course, to interpret seismic lines and do active and passive types of remote sensing as it applies to petroleum exploration. In terms of more pure geology positions, there's a couple options for you. The first of these is the position called exploration geologist. This is actually what I was doing when I was working in a petroleum company when I was still a student. I was an exploration geologist for a while, and in this career move, you are responsible for identifying potential sites for petroleum accumulation using different techniques, like looking at surface outcrop or handling electric logs and applying them to, say, geophysical surveys. Okay, so basically you're responsible for an awful lot of the point source information although you are expected to actually start tracing out laterally. When I worked in the petroleum field as an exploration geologist, most of my emphasis was in terms of interpreting electric logs. They are more convenient to deal with rather than the large seismic sections, in part because they are we have data for just about every well that's ever been drilled, and it was just a little bit simpler, especially for somebody who was new to the career or new to the field, to actually interpret and understand. And you were responsible for dealing with interpreting single wells as well as tracing them laterally into other fields and all. So it was a relatively fun thing to actually go and do. Now, what you ultimately are expected to do is to develop potential plays. A play is a site that you have recognized or have identified as a possible oil or natural gas producer. And one of the things that an exploration geologist does is to look at areas where there may be new fields or where older fields can be exploited and redeveloped. It was a fun job, I'll say that, but I'll tell you that it gets to be kind of scary after a while, because in part your potential for advancement or survival at a company is dependent upon how successful you are. I remember we had $1 million geologists, the geologists that were responsible for finding huge new deposits that were multi-million-dollar things. And when you are sitting on your first well, when they're drilling the first well that you have recommended that they drill, you get the heebie-jeebies because you want it to be successful, but by the same token, you're not going to be 100% right all the time. The career possibility for geologists in the petroleum field is better classified as a developmental geologist. Now, these geologists start with a well that has shown potential, call it a discovery well if you wish, and they follow along with a detailed seismic survey. And what you end up doing at this point is to more or less develop the site by proposing new wells and trying to find areas where you can actually pump a lot more oil out of the region without depleting the reservoir or destroying the reservoir properties too much. This is a job for people that are interested in stratigraphy, sedimentology, and structural geology, because again, a lot of the trapping mechanisms are structural in nature. Now, there are other career pathways for individuals that are interested in petroleum geology. One that up until really even a few years ago was still a potential career move was research geologist. And again, I did a little bit of work with this when I was working in the petroleum industry, and I loved it. I mean, here you had a chance to do everything that you would do as an undergraduate student. I spent a lot of time under a microscope looking at the porosity of various materials below the subsurface. Most oil companies have kind of gotten rid of their research components because it's proven to be kind of too expensive to keep researchers online when you can access universities, graduate students, and even private consultants whenever you needed to have somebody to do some research. A similar thing happened with the paleontology side of things. In the past, oil companies had a lot of micropaleontologists. And a lot of those positions have now not been kind of filled because it's convenient when you have a problem or you need someone to do some assessing from paleontology nature to more or less go to the consultants and let them do it for you. So you pay them a lot of money, but then you don't have to worry about paying for them all the time when they're not actually necessary. All right, now I left this slide, okay, because we tend to think that everybody sees eye to eye whenever it comes to everything, because there is a right answer and there is a wrong answer. I don't think that's true in many professional fields that deal with risking and trying to find sources of potential economic success. when you're dealing with a non-exact science. So when petroleum companies are starting to look around for where they can drill for new reserves, there's a lot of disagreement between the people that are working for the company in terms of where they should actually drill. All right? And this happens to all of us. You'll have a property. One geologist will say, we need to drill on it because I think there's the potential for oil here. Another one that's worked on the fields in this, the same degree as the proponent who wants to drill might say, no, I don't think it's going to be potentially viable at all. We're going to lose money. So you end up having two opinions, and it's up to the managers to decide which opinions are the ones they're going to go for. So in much the same way as lawyers will argue legal cases before a judge, in the petroleum industry, you'll have geologists that will argue their more or less positions and let the manager make the decision as to which way they go. But the important thing to note here is that if we're not always in agreement with each other, that means that we're never going to entirely always be correct. Now, admittedly, you might be the only one who's always right every single time, and the people you're arguing with are going to be wrong every single time. But if you're wrong every single time, there's a good chance you're not going to be staying with that company very long. In which case, you're replaced by somebody else who might be a little bit better in their predictions, and there's still going to be disagreement. Okay, so if everybody agrees all the time, chances are they're not really doing their job as well as they should be doing their job. Okay, now while some things are debatable in petroleum geology, there are certainly some things that are not. There are things that we can agree on, some variables that are consistent or are constant in their behavior. For example, with increasing depth, we will find that rocks below the surface will contain increasingly more varied types of fluids. In fact, the rocks below the subsurface are usually enriched in fluids, be it water, oil, natural gas, or in some cases hydrothermal fluids. Water is by far the most common fluid that occurs in the subsurface. And while we normally think of water in terms of being an important component that someone like hydrogeologists like Jim Connors would look at, it's important that you realize that water is also an important variable in petroleum geology. This is often the mechanism by which fluids or pore fluids exert pressure, and it's the pore pressure that's important for regulating the behavior of how oil and natural gas behave. So water is important to petroleum geology as it is to hydrogeologists. There's some things you should note about the water, though, as you go into the subsurface. Now, this diagram here shows you some of the variables that will change with fluids as you go at depth, or to depth. The diagram that you see off to the right deals with salinity, and I'll get to that in just a second here. Okay, so the major things that we can all agree on in terms of how fluids behave is that the deeper you go, the hotter it's going to get because of the geothermal gradient, and obviously if the fluids are hosted in rocks, then they are also going to be increasing their temperature as well. You'll also find that the fluid pressure generally increases. It doesn't always increase at the same amount, and there are some areas where the pockets of fluids may be overpressurized, or in some cases underpressurized. But for the most part, as a general statement, fluid pressure will increase with depth. Water salinity also generally increases with depth, and that takes us to the diagram that's off to the right. What you see here is a chart that relates the total solids in parts per million, and this would be the dissolved solids in parts per million. It would include things like sodium chloride, calcium carbonate, and other somewhat soluble minerals, versus depth, in this case in feet. So you'll see here, if you look at a depth of around 1,000 feet below the surface, the average salinity of fluids at this level, water at this level, would be about 100,000 parts per million. Getting down to about 5,000 feet, you see that it gets up to about 210, 215,000 parts per million. Now again, this is kind of like idealistic. There are some situations where you're going to find pockets of
saline water. In fact, there have been many instances when oil companies have been drilling at depth looking for oil and natural gas, and they inadvertently come across a pocket of fresh water, which is not a problem because if it's suitable for drinking purposes or irrigation purposes, you can still make a profit out of pumping water, it's coming from thousands of feet below the surface. And if the pressure is high enough, it will be a free-flowing, almost like an artesian well type of situation. With additional depth, the water density will increase, and that is shown in this next diagram here. And what you've got is a chart that's showing you relating water density changes to depth again. And this again is fairly consistent. I mean, it makes sense if you think about it, because if the specific gravity, which is how we measure the density of water, is dependent upon the concentration of dissolved components in it, the more saline the water gets, obviously the more dense or the higher specific gravity the water is going to have as well. In addition, from the important point of view from petroleum, oil density tends to increase as you go at depth, and this is the density or the specific gravity of the oil itself. And mudstone bulk density will also increase, and this is an important consideration when you're talking about either the source of materials or ultimately the mechanisms by which oil is restricted in its flow. In other words, these would be things that would be resulting in trapping mechanisms and cap rock mechanisms. All right, now one more diagram, and we really probably should be going into a little bit more detail in terms of the properties of water. And if you get into the petroleum industry, if you are going to be trying to interpret fluid content by looking at electric logs, it is important that you understand how you can identify fluids by looking at different properties, say like resistivity. So this chart that you see here now, which comes from a standard well logging short course, is a chart that relates salinity to resistivity and various other properties. And I don't expect you to be able to see this because A, it's turned around sideways, and B, it's a very, very, very small diagram of a very complex chart. In terms of fluid dynamics in petroleum, salinity is the most important water property that we have to deal with because it will be controlling some of the electrical properties of a rock. If you have a very saline fluid, a very saline water, it will reduce the resistivity to almost nothing. And resistivity, of course, is one of the properties that we can easily measure when we're doing downhole analysis of logs. So understanding how salinity controls resistivity of a fluid is important. We generally regard the salinity as being the total concentration of all the dissolved salts, so the TDS component of things. All right, and that would be measured in parts per million. And even though the salinity may result from a combination of things like halite and dissolved calcium carbonate, and even in some cases dissolved sylvite and other soluble ingredients, we normally equate it to sodium chloride because that's the most common of the soluble electrolytes that occur in fluids. So most of the charts we're going to be dealing with will have an equivalent component that does it to sodium chloride. All right, now this next chart is, again, it shows you how water salinity varies from reservoir to reservoir, from formation to formation. And as I tried to explain to you earlier, the salinity of water below the subsurface generally increases with depth, but there are places where you can find fluids that are more or less not saline at all. They're particularly associated with sandstone aquifers. So the actual salinity can vary from about 0 parts per million, which is absolutely fresh water, to about 300,000 parts per million. Now, if you're not familiar with the parts per million expression, seawater is typically around 35,000 parts per million, or if you wish, 35 parts per thousand. So we're talking about pore water salinities that can be almost 10 times the salinity of seawater. And when they have concentration like this, they have the potential for doing very interesting things diagenetically. There can be changes in mineralogy, which is not something we really have to be concerned about in a geophysics course, but it does introduce some interesting possibilities. Typical salinities in the subsurface go from around 2.5 to 3 times seawater values to maybe about 4 times seawater values. So call that 80 80 to 100,000 parts per million. And this is, again, something that's going to be controlling the properties of some of the electrical properties, which we can measure relatively easily in the subsurface. And it does mean that if you have a salt water aquifer, it's largely going to be saline in nature, and that means it's going to have no resistivity. Oil, on the other hand, if it's pure oil or pure natural gas, tends to have quite a bit of resistivity. And that gives you the idea that on resistivity alone, in some cases, you can get a feel for the type of fluids that you might have in the rocks. Now, it's not that simple. You have to consider other variables in here, but that's certainly a first approximation in terms of reservoir characterization in terms of the fluids. All right, now turning our attention to petroleum. I guess it's about time we actually define what this stuff is, the black gold component that all economic geologists that deal with energy are eager to find. If you find a good petroleum deposit, boy, you're in the money for a while. So perhaps we should actually define what petroleum is. The official definition of petroleum is a natural substance that is composed of organic material in both a solid or semi-solid state, liquid state, or gaseous state. All right, so it is basically the remains of once living organisms. And there's two different classifications, two different divisions. Crude oil. Crude oil is the stuff that you get out of the ground, and what this is basically a mixture of all these different components. Or if you like my definition, crude oil is the type of material that will leave a residue, a solid tarry mass, after you distill it. And distillation is where you actually chemically crack it by which to extract the various components. We'll talk about that in just a second. Or if you're lucky, you'll get a gas condensate. Gas condensates are, in some ways, are the best thing to find. They're not really all that abundant in nature, but these are things that are the lighter fractions. They flow more like water, and they're almost pure organic compounds that can be distilled into very useful materials. Now, if you're wondering what's going on in this figure here, I couldn't resist including this. This is an image I found a couple of years ago, and apparently in some parts of the former Soviet Union, crude oil immersion is considered to be some sort of a therapy component to it. I don't know what kind of miraculous cure you're going to get out of covering yourself in crude oil and then having it scraped off. Maybe it's an exfoliant of some sort. I do know that I would not do this because crude oil also can contain some pretty nasty things that I would rather not be seeping into various orifices of my body. But apparently, if you're in this area, it's something that you will pay money to do. Yeah, okay. All right, now changing our venue now to start talking about the actual chemistry of petroleum, and this is something that goes into organic chemistry, and it's the safe organic chemistry. It's the practical organic chemistry. You don't have to worry about pharmaceuticals or anything here. Now, this is basically organic chemistry as it applies to naturally occurring organic compounds. And again, you have to remember that oil, petroleum, natural gas was all originally derived from organic material, and when it breaks down into either semi-fluid organic compounds or fluid or gaseous compounds. Now, the simplest arrangement of these organic compounds will give you molecules that will have an arrangement of carbon and hydrogens. And there are different series of organics that we need to discuss here in terms of the arrangements of these various components. All right? So we call these the various isomer series. The first isomer series, which are the easiest to discuss and to characterize, are the so-called alkanes, or they're also known as the paraffin series. These are the ones that we normally think about when we're talking about basic organic compounds. They involve carbon and hydrogen and not an awful lot of other stuff. So here you have an example of two of the simplest types of alkanes. Methane, which chemical formula is CH4. We have one carbon ion surrounded by 4 hydrogen ions, forming a classic, very simple alkane here. And methane is, of course, a natural gas. If you look to the right of the methane, you'll see the molecule for ethane, which is 2 carbon molecules stuck together with hydrogen surrounding them. Now, this is the nice thing about the carbon molecules, or the organic compounds in general. Carbons can form long chains of molecules, and this, of course, is the secret behind all organic substances, including the organics that make up your body. Okay, so these are the shortest chain alkanes that we have, one with only one carbon and with two carbons, and of course it goes on and on and on. The general formula for this series is CnH2n plus 2. All right, so the normal alkanes give you what are called the straight chain molecules. You can also get isoalkanes, and these are alkanes that have cross branches of carbons, and they can get very complex and highly variable, where they can start branching off in different directions. I've left off the H components of these molecules just for clarification purposes here, and you can see that there's an example of nonane there that's got 9 carbons in a straight chain, and then you have nonane, which has the same more or less formula, but it's got a different arrangement of the carbons. And again, you should remember from basic chemistry class that we tend to name the carbon molecules according to the number of carbons it has. So N-nonane, which is the straight chain one, has 9 carbons. The I-nonane has 9 carbons arranged in the fashion you see there. And of course, if we had 8 carbons, that would be octane, and octane is our primary gasoline component for fuels when we go to fuel up our cars. Then we have the cycloalkane series. Now these are carbons that are arranged in a ring structure with a single bond between each of the carbons. All right, so what you see here now are 5 ring structures called cyclopentane. There's also 6 ring structures called cyclohexane. Now please note, this is important, there are no double bonds in any of those molecules. The general formula for these structures is CnH to the 2n. Now the reason why I don't want you to confuse the hexanes with this next ingredient is because the aromatic series starts having double bonds as part of the ring structure. The 3 molecules that you see here, benzene, toluene, naphthalene, and there are others that represent this grouping, including xylene, are among the most important components in petroleum, and in some ways among the most dangerous. Benzene, for example, that very simple benzene structure that you see portrayed as 6 carbons and 6 hydrogens radiating out from it, is a very well-known carcinogen. And up until about the 1970s, 1980s, benzene was a common chemical that you could buy in drugstores. It was used for, I believe, as for removing adhesives and various things, and we use benzene as a heavy liquid in some cases too. We now know better than that. Benzene is carcinogenic under very, very, very dilute concentrations, and in fact, this is one of the aromatic compounds that we don't think that there is any safe levels of, so you have to be careful about that. Toluene, xylene, and naphthalene. Naphthalene is the main ingredient with by which mothballs are made. Are also a little bit on the suspicious side here because of the potential ring structure that you're looking at. All right, so these compounds are also common ingredients within crude oil. Now, getting back to the idea of crude oil. Crude oil classification, in terms of how they are classified, we do subdivide them, was originally proposed based upon the composition of the isomers, plus a little bit of things like nitrogen, sulfur, and oxygen. And these are normally referred to as the NSO components. What you see in this diagram is a standard ternary plot where you have the 3 N members here, where you have the N and isoalkanes, the cycloalkanes, and the aromatic compounds that make up the bulk of crude petroleum. And you'll see also the fields that have been designated here in terms of what their actual names are. Now, I have to admit, we don't, for the most part, use these names in petroleum geology. We use a different way to classify them. But from the purely chemical point of view, or the inorganic, organic side of things, then calling these things paraffinic or naphthalenic oils has its advantages, because what it allows you to do is identify fields where you get different mixtures of these 3 different components. All right. If you analyze oil, though, what you'll find is it's surprisingly consistent in terms of its overall composition. What you'll find is that most oils consist of about 83 to 87% carbon, about 12 to 15% hydrogen, and the nitrogen, sulfur, and oxygen content is usually less than about 5%. All right, so this is the range of elemental compositions that oils will exhibit. So while the composition is the same in terms of basic atomic ingredients, the major difference between the oils is whether we have straight chain carbon molecules or aromatic compounds or cycloalkane compounds. Okay, and that's ultimately what's going to be controlling a lot of the different oils that are being produced. Now, for oil in general, what we'll find, and again, here's some general understandings of how the oil changes. For oil of any series, for example, if you're talking about the cycloalkanes or the just the alkanes in general, you'll find that as a fluid, viscosity will tend to decrease as the temperature increases, or alternatively, if you heat the oil up, it will tend to flow a lot more like a fluid. This, incidentally, is the trick behind extracting heavy oil from the oil sands of Canada. They are a tarry substance in their natural state, so what you end up having to do is heating them up to extract the oil and get it to flow out of the sand. Viscosity increases with increasing fluid density, and again, the more dense the oil is, the more viscous it's going to be behaving, and you'll find in just a minute that a lot of viscosity is controlled by the nature of the ingredients that make up the oil products. And the viscosity increases with increasing carbons per molecule. So in other words, carbon-rich fluids tend to be more viscous than carbon-poor fluids. Another consideration. And the thing to note is that when you're dealing with oil production, oil extraction, there are better combinations of carbon compounds than others in terms of ease of getting the stuff to the surface. Now, ultimately, all this is leading us to the ability to predict and identify oil, crude oil, based upon its density. And we identify the density or relate the density to so-called API gravity units. And API stands for the American Petroleum Institute. So they're the regulators in terms of classifying oils. The API is expressed as this relationship: 141.5 divided by the specific gravity of the fluid minus 131.5. And I don't know where they got this from. All I do know is that it will produce a series of oil types, and these are the classifications that we're more likely to use in petroleum exploration when we're talking about the grade of the oil we're dealing with. Okay? So here are the various grades of petroleum. Condensate, the most highly sought after component of oil, has an API of greater than 55 degrees. Light oil goes from 31 to 55 API, and there's a specific definition in terms of the viscosity here too, which we don't have to really worry about at this point. Medium oil goes from 22 to 31. Heavy oil goes from 10 to 22, and extra heavy oil is less than about 10. Tar sands fall within the extra heavy oil to medium oil divisions and are characterized by very high viscosities. It makes sense if you think about it, because the oils are not flowing. All right, and from this we extract all of the various types of materials that will ultimately make up the fuels and the various organic compounds that we refine and sell on the market. Now, the table you see there is a idealized composition of what a 35-degree API gravity oil would produce. It would produce gasoline, which would be defined as the C5 to C10 component of the organics. You get 27% of that oil would break down to give you gasoline. Kerosene, which is defined as the C11 to C13 fraction, you get 13%. Diesel fuel, C14 to C18, is 12%. Heavy gas oil, C19 to C23. Lubricating oils, and again, what's happening is we're getting more and more and more viscous as we go towards the bottom. The lubricating oils, C26 to C40, about 20%. And the rest of the stuff, residuum, which is the really tarry substances that may not have any practical use whatsoever, 18%. So when you get a barrel of oil, it's not going to give you 100% gasoline from that. It's going to give you literally only about 1/4 of gasoline. And of course, the heavier the crude oil, the less of these different divisions you're going to be able to get out of it. And of this, if you were to analyze it for this particular oil and this particular substance, you'd find that 25% of the oil was paraffins, 50% with naphthalenes, aromatics were 17%, and the asphalt components, which we haven't talked about, is about 8%. Okay, so that gives you an idea of the breakdown in terms of what you can get out of oil. I think that's enough about the chemistry of oil. Now I suppose we should turn our attention to how oil is actually produced. This particular slide shows you a very nice sequence of shots of black shale. And black shale, if you remember from your Geology 111, is an organic rich shale. And as far as petroleum is concerned, it is also a source rock. Petroleum is primarily produced through alteration of organic material that is found in rocks like this. And almost all of the source rocks start off as being black shales because they're very fine-grained materials. And if you think about it, it stands to reason that fine-grained organic material is more likely going to be concentrated in fine-grained sediment, low-energy types of environments that are anaerobic. You need to have an environment where fine-grained material can be collected. That means low energy. And also where oxygen is removed from the environment. That means anaerobic. So this is a typical source rock. The thing to note is that oil rarely, if ever, originates in the reservoir in which it's found. By this I mean that it's very unlikely for oil to get concentrated in the very place that the organic material was in the first place. Almost always, oil will form through the alteration of organic material after it has moved from the source into some sort of a reservoir type of structure. In other words, it gets concentrated through secondary migration. Now, this is one of the key concepts of petroleum geology in terms of tracking the oil. You need to find the source rocks, yes, but you also need to find a suitable place where oil can be concentrated, oil or natural gas, as we're talking about them collectively here. Some other interesting things. There seems to be no obvious difference between the composition of petroleum and rock age. And you know, at first you almost think that the older the oil is going to be, the more waxy or tarry it will be, but that does not seem to be true. There are plenty of low API of oils that are formed throughout geological time, at least throughout the Phanerozoic. There tends to be more waxy oils in Mesozoic age rocks and maybe a little bit younger rocks than that, and there's some speculation that this may be due to the fact that there was more extensive terrestrial vegetation at this time. And we'll talk about the ultimate source of the organics in just a few minutes. Now, where oil comes from is going to be organic material. Specifically, it'll be things like proteins, fats, waxes, humus. Anything that is organic in nature that has carbon molecules in it can ultimately alter to form organic compounds that are capable of migration. In other words, becoming fluid or gaseous in nature. You know, I'm guilty of this as much as anybody else is. I tend to, when I'm talking to students about where oil comes from, I'm almost always talking about marine source rocks. And while it's true that the majority of oil deposits that I'm personally familiar with did have a marine origin ultimately, there is plenty of evidence to suggest that there are terrestrial source rocks as well. Plants will give rise to useful petroleum components, especially natural gases. It's one of the reasons why when you see coal beds, there's almost always going to be natural gas associated with them. It is true, however, when you look at the breakdown of marine organic material tends to, it's more of an animal type of carbon. It tends to have higher hydrogen-carbon ratios than does plant material. And this means that you're going to get products that are going to have a higher hydrogen concentration in them, and ultimately that's what kind of shifts you from more of a coal type organic product into the potential for a liquid petroleum, crude oil, natural gas type of deposit. And also it's true that marine organic material tends to be more aromatic in nature than plant material does, and this leads to having more aromatic compounds in some of the oil fields that we find around the world. Now, this diagram is it's dealing with diagenesis, and diagenesis is the chemical and physical changes that take place to substances after after they've been produced. But what I've done is I've shown an inset of a refinery, specifically a cracking tower, and these are one of the basic components of oil refineries around the world. And what a cracking tower does is more or less emulate what happens in nature. In cracking, whether it's artificially induced like we see here, or whether it's happening naturally underground, what you end up having is a gradual increase in temperature, which starts to take these long-chain organic molecules and breaks them down into smaller and smaller divisions. And if you look at the inside of the cracking tower there, you'll see that we have 4 different plates. The blue plate, which is the lowest down, involves fluids that are condensing at the highest temperature, because there's basically a heat source at the base of that cracking tower. So the heaviest oils, the ones that have the highest API, tend to become less gaseous at a higher temperature, and those are the things that end up having longer chain molecules. So they become the lubricating oils. The fuel oils and diesel oils tend to form at a slightly higher temperature. They're indicated by the purplish color. Kerosene is the pinkish color, and of course gasoline tends to condense at the highest temperature. That's right. So it's the one that is at the highest there. And of course, anything that does not condense, if it is a short enough chain to be a gas, comes off the top. And in most refineries, it's simply burned off. I mean, we could collect the stuff, but really the amount of natural gas produced this way just doesn't make it worthwhile to actually funnel it through to some sort of a collecting thing. It's just best to burn it off. All right. So this type of process also occurs in the subsurface with organic compounds, except what happens here now is you're starting off with the more solid materials, solid organic stuff from marine organics, and in some cases from plant organics. And you start heating things up. Those long chain molecules that might be 40 or 50 carbons long will start breaking into smaller and smaller chains, and ultimately they will go from being solid masses into increasingly liquid and ultimately gaseous carbons, hydrocarbons. And of course, once they become liquid or once they become gaseous, they're capable of migrating now from the source rock into another body rock. Call it the reservoir rock if you wish. Okay. Some other things to note here. This little diagram on the side is just more or less showing you the different types of things that can happen with depth, and depth here is related ultimately to temperature. Okay, so the deeper you go, the hotter things are going to get. And it's important to note that temperature is an important variable here. It is the temperature that is going to regulate the amount of thermal cracking that is going to take place. Soluble products, and there are plenty of soluble hydrocarbon products, are lost almost immediately through diagenesis. They just get washed away by any water that happens to be in solution. Insoluble products that ultimately will not break down, will stay solid, are simply called kerogen. And of the kerogen, we recognize 3 basic types. And I'll go to those in just a second. First of all, just one last comment about the diagram you see here. As you look at the column that is to the far left, that's titled biogenic molecules, you'll see what's happening here is that you start breaking things down at around 10 meters of depth, at least according to this diagram. You'll start to see humic substances breaking off into methane. That's when you start getting the first of the losses of material, and that will, of course, be gas that's generating going somewhere else. Once you get down to about 1,000 feet to about 10,000 feet, you're probably getting oil being produced at this point, as well as additional natural gas being produced. Below about 12,000 feet, you start seeing this thing that says basically dead carbon. And if you look at the column on the right, you'll see that that is where they start getting into the realm of metamorphism. You have to be a little bit careful about that, because it really depends upon the geothermal gradient as to when that breakdown takes place. The important interval that we're going to be talking about, the petroleum window, is not something that is absolutely fixed. It depends upon the thermal heat flow of a basin. As you'll see, it's going to be variable as to where it's going to be occurring. Where we live along the Gulf Coast, our petroleum window starts at around 5,000 feet and goes down to about 14,000 feet, plus or minus a few thousand feet. We'll talk more about that in just a little bit. I have a better diagram to show you in just a few minutes. Now, first of all, let's talk about those different kerogens that we were talking about before, okay? Type 1 kerogen is derived from organic material with lipids, and we don't have to get into the biochemistry right now, but let's just assume that this stuff is dominantly marine that has hydrogen-carbon ratios greater than about 1.5. There are very few aromatic compounds associated with this particular type of kerogen. This is a very good source for oil and natural gas. Now, the inset photograph you see there is a polished thin section that is showing you kerogen. It's the brightly reflecting products you see there. A reflected light microscope is needed to identify these products. The reason for this is that organic material kerogens are opaque, and in order to identify what they are, you basically have to take a thin section, polish it, and then use reflected light. And the degree of polish, degree of reflection along the polished surface will give you an idea of what type of kerogen you're dealing with. Now, last time we taught this course back in, I believe it was 2008, that was all we could say about this particular technique for identifying organic material. But since that time, we've got ourselves a reflected light microscope, which means that there is the possibility of actually doing some studies now on organic material. So if anybody's interested in maybe doing a directed studies where you look at kerogen materials in cores and trying to characterize them and coming up with a study that might have some relevance to the petroleum industry, come see me and we'll see what we can actually do, because I think it is possible now that we can actually start studying kerogen types. Type 2 kerogen is also derived from marine organic material, but here the hydrogen-carbon ratios are a little bit lower, less than 1.5, and there's a lot of aromatic rings. This is still a good source of petroleum and natural gas, and you'll see in inverted quotes here I say a quite good source. That's because the reference material I was using obviously was written by somebody with a British accent, because they're the only people that would say it's a quite good source for oil and gas. And lastly, type 3 kerogen. This is the coal-based material, okay? So these are terrestrial plants where you end up having a very high carbon ratio here. And when you have a high carbon ratio, it tends to drive maturation into pure coal or pure carbon components. It's not a particularly good source for liquid petroleum, although there is some evidence to suggest that some liquid petroleum deposits are generated from what was originally terrestrial material, but it will generate a significant amount of natural gas. And like I said, depending upon what you're looking for, whether it's gas or whether it is oil, if you can make a profit off of it, who cares ultimately where it came from? All right, now again, let's get back to the whole idea of diagenesis and alteration. Okay, I'm going to show you a couple diagrams here that you don't really have to worry too much about, because they basically are showing you how hydrogen-carbon-oxygen ratios change over time. Now, this first diagram is showing you how maturation takes place in petroleum. Here you see the type 1, type 2, and type 3 kerogens plotted up against the hydrogen-carbon ratio on the vertical axis and the oxygen-carbon ratio on the horizontal axis. You'll see that as time goes on, burial, and the arrow that is showing you in red there is showing you the burial direction, all of the organic compounds more or less come together. And this is because with maturation, what you end up doing is converting the oil into a common substance. Okay. Now, the further down you go, the deeper you go, the more it's going to break down to essentially the shortest chains, to ultimately getting into things like methane, and if you're dealing with something with a very high carbon-hydrogen ratio, then you're going to start getting into coal, etc. This diagram here also shows you how maturation is controlled by temperature and possibly also pressure. I don't claim to understand exactly how some of these organic reactions work, and I think it's very hard to separate the pressure from the temperature when you go at depth. But the thing to note here is that there have been a lot of studies looking at how organic material is matured and how it varies through different properties, of which temperature and possibly pressure are the two most vital components. Now, this diagram is far more important because it is much more intuitive. This is the type of thing that a geologist can understand, because what it does is it relates depth to ultimately what is happening to organic material. So as you look at this diagram here, what you're seeing is the different type of material that is being produced according to depth. At the very top, going down to about 500 meters, you see a field that is called biogenic methane. Now, this is the type of material that will be produced early during the earliest phase of diagenesis if you have anaerobic conditions as a byproduct of the breakdown of organic material. Once you get below 1,000 meters, however, what you're going to start to find is that the organic material itself starts to break down. So the biogenic methane is being produced by, say, reducing bacteria as it eats or digests organic material, but below that window you start actually breaking down the organic material. Now what you're going to find is that as you go deeper and deeper and deeper, you're going to find that the amount of oil being produced, shown in the green field, increases to a point and then starts to diminish. You'll also see that natural gas starts to form, again, fairly early, but really doesn't become much of a dominant player until you get below the oil peak. Now, ultimately, in this diagram here, which is related to depth, between about 2,700 meters and 3,600 meters, where you see those dashed lines, that is showing you where oil is being produced primarily. This is the so-called oil window, the petroleum window, if you wish. These are the depths, according to this particular area, according to what the geothermal gradient is, where the temperatures are just the right amount, that you're going to take these long chain organic molecules and break them down into chains that are between about C5 and C10 in length. Now, if you go any deeper, you start getting into hotter and hotter temperatures, and then what you'll find is that the amount of petroleum starts to be reduced, and you start to find an increase in the amount of natural gas that is being produced. So what we're looking at here now is that we have oil that is produced under a certain temperature range. If it's too cold, you don't get any oil. If it's too hot, you don't get any oil. So ideally, you want that temperature range between about 75 degrees Celsius and maybe about 125 degrees Celsius. That's the perfect temperature for crude oil to be produced from organic material. If it's too hot, you get natural gas. And this, of course, is related to depth. Now, where we live, in our area, the petroleum window is about between 5,000 feet and about 14,000 feet. Anything lower than 14,000 feet and you're into primarily natural gas. Anything above 5,000 feet and you basically don't have anything at all, at least for the old rocks. I'm not going to talk about the Miocene oils around here because that's a different thing entirely. But we have a lot of production platforms off the coast, just south of Mobile, south of Dauphin Island, and those things are all tapped down to about 20,000 feet. Between 18 and 20,000 feet below the surface. Now, that is very deep. It is well below the petroleum window. In fact, all those wells are producing natural gas. But if you come to the north, if you go north of Mobile, into Escatawpa County, into Conecuh County, into those areas of Alabama, you start getting into shallower reservoir rocks. In those depths, the wells are drilled down to about 14,000 feet, 12,000 feet, and they are well within the petroleum window. So those wells are actually extracting crude oil, and they're not that far north of us. That's because there's a very shallow dip. And a shallow dip, whether it's 1 or 2 degrees, is still sufficient to take a rock and elevate it or bring it closer to the surface. And once you're within that petroleum window, there's plenty of opportunity to get oil, and in some cases natural gas. And the reservoir that we are drilling through here, which we will be talking about in a number of times in this class, is of course the Smackover Formation, also the Norphlet Formation, which are two very important oil and natural gas producing formations in our part of the world. Now, despite what I've shown you here in terms of a diagram, I think it's safe to say that there's still not an awful lot that we know about petroleum formation. I mean, we know the basic things, but boy, there are a lot of questions. For example, what is the roles of mineral catalysts in this whole production? And by this we mean, do clay minerals play a role in breaking down the carbon? I mean, there's a lot of catalytic reactions that take place. There's some speculation that maybe minerals themselves may augment the reaction. We know that clays and in this case nickel ions can cause carbon molecules to crack at much lower temperatures. And indeed, this is one of the things that we've used to refine some petroleum using things like Fuller's earth. We also aware that when you're talking about petroleum, if it's starting to migrate, if it's moving through different layers, it's going to be coming in contact with different clay minerals, different minerals in general. So we may actually have situations where, in some cases, crude oil production or cracking is being augmented by just traveling through a different sequence of rocks, whereas rocks that might be further lower, that are lower, may not crack as much, even though they're in warmer temperatures and all. So I guess ultimately what we can conclude is that even though diagrams like this relate production exclusively to depth/temperature, there may be other variables involved in this, and it may explain why we start finding oil at different depths in different places. Yeah, it may be associated with the geothermal gradient, but it may be associated with other things as well. Okay. All right, now let's talk about migration of petroleum. All right, migration, again, when we talk about this type of thing, especially when we do it at the 100 level, we make it seem so blatantly easy. You have a source rock, you heat it up, the organic material goes from a solid into a liquid, migrates until it gets trapped. Voila, you have oil, you drill a hole, you get the oil out of the ground, you make a fortune. All right, that is not exactly how this is thought to work. We have migration, yes, but there's primary migration and there's secondary migration. Now, secondary migration is more or less what I just explained to you. Once you get the oil mobilized and it's in a rock that it can move through pores, and then it will concentrate, say, underneath an anticline like you see in this diagram. And it's important enough that we're going to concentrate this aspect of migration in an upcoming lecture. What we want to concentrate on right now, though, is primary migration. And this is the first phase of movement out of the source rock into the surrounding rocks. And if you think about it, we got a problem here. Because we said earlier that organic material is fine-grained. So it tends to be concentrated in fine-grained sedimentary rocks, hence black shales. Well, black shale is a pretty tight rock. By tight, I mean it doesn't have much porosity, doesn't have much permeability in it. So how do you get oil out of a tight rock? How do you get oil out of mudstone? Well, this is one of those mysteries, and I don't know if we actually know very much about it at all. There have been several things that have been proposed. For example, solution. Is it possible that you can take organic material, dissolve it in water, and have the water pass through the clay through various types of processes like osmosis or something like that? All right. Well, the thing is, oil, even under temperatures of that are fairly hot, and certainly at the temperatures that we believe are in existence in the subsurface where oil is forming, is very insoluble. I mean, think about it. Oil floats on top of water, right? And while there's some soluble components that get washed away early, most of the oil that we have got to worry about moving has a solubility of less than about 50 parts per million. Now, there are exceptions. Benzene and toluene are things that are rather soluble, which is one of the reasons why you have to worry about benzene and toluene getting in groundwater along contaminated site, as is methane. But again, we have a problem because the temperatures are too low within the petroleum window to get a lot of these things dissolving out. So overall, I think it's safe to conclude that this is not thought to be an important transport mechanism for primary migration. We have to think of something else. Here's something that has been suggested: colloidal transport. Colloids are basically molecules that are spherical in nature and behave like soap. Soap particles are useful in terms of cleaning surfaces because they have these kind of like free radicals at the end, which can attach onto other ions, say on the dirt side of things, and more or less pull them off of a surface, and because they're soluble, they'll be dissolved in water and washed away. I mean, that's why soap is effective. When you put shampoo in your hair and you're washing your hair, it gets nice and slippery, and basically what's happening is that you have a colloidal solution that is more or less stripping off the dirt from your hair. Now, it doesn't work if you're in a situation where you have not heavy water, sorry, don't wash your hair in heavy water. If you're in a situation where the water is hard, because hard water has a higher than average concentration of cations like calcium and magnesium, and those cations, which are positively charged, stick to the soap and more or less bind them up. Net result is the soap doesn't clean effectively, and it feels like it's sticking in your hair, and you never get things clean. So basically, colloidal transport more or less is thought to be one possible mechanism where you can more or less transport hydrocarbons through fine-grained materials on the backs of these so-called soap bubbles. But you don't get a lot of these things, at least the micelles, which are the things that are thought to be possibly involved in the transport of hydrocarbons, just don't seem to be that abundant. And we still have to move a lot of hydrocarbons out of the shales into the surrounding more porous rocks where it can be moved by secondary transport. So again, we don't think that this is an important variable in transport of sediment. Diffusion is one additional type of mechanism that has been suggested. Diffusion is where you more or less just have products moving through boundaries and surfaces. It's an important regulatory control we have in terms of ion exchange films, etc., where you allow certain molecules to pass through barriers to get to the other side. But diffusion of hydrocarbons through rock is incredibly slow. Methane can do it, but it's not, again, all that abundant. It explains why we can get some methane in just about every type of sedimentary rock. But it can't really explain the vast quantities of methane or of liquid petroleum that we actually find in the rocks surrounding it. And frankly, if you have a molecule that's too big, and I believe that anything bigger than about a butane is too big to go through this, are not going to be moved at all. So once again, we don't actually have any viable way that diffusion can be a primary way in which things get through. Now, gas phase migration, now basically what this is that you dissolve hydrocarbons into, liquid hydrocarbons into a gas, and then pass them collectively through shale materials as a dissolved organic component into, dissolved liquid component into a gas phase. This is a viable option, and it has been shown that this can happen at depths, say around 10,000 feet. You can actually transport things like decane and methane together as a single gas phase. But if this were something that were a real major thing that was happening in most oil fields, then what you would find is that the gas-oil ratio would be much higher than it is in most oil fields. So when we look at oil fields, we'll find that there's a lot more oil than gas to explain this type of transport as being the dominant process by which oil can migrate out of tight rocks like black shale. So that leaves us with essentially the idea that the oil is migrating somehow out of rocks as a liquid phase. This is thought to be driven by microfractures. When you start compressing rocks and burying them, the stresses of confined burial are going to start to cause pressures to build up in the rocks. And liquids can actually exert a certain amount of pore fluid, which can cause fractures, or in this case, microfractures. Because some of these fractures may be on the order of only a few microns across, or less than that. It's been shown that water is capable of flowing along a microfracture that is about 500 nanometers in diameter. That is really, really, really tiny. We have molecules and unit cells of crystals that are much larger than that. So it's possible that when you start having fluid pressures building up in shales, they'll result in a whole bunch of these microfractures that will network together and allow the liquid to pass along the microfractures as the sediment is being progressively squeezed and out into the surrounding rocks. So right now, without knowing anything else, I think it's best to conclude that when you get primary migration, the primary migration is being driven by fluids slowly escaping through the source rock into overriding more porous rocks, and from there they can move much more rapidly and be concentrated in much larger holes where, if we're lucky, we will come around with our drill rigs and find good concentrations of these things sometime in the future. So ultimately, source rock migration starts off as being liquid and along these microfractures. Now, the microfractures are really quite tiny, and you may not see them in all the organic rocks that you have, but ultimately it comes down to the idea that we're talking now about the fluid pressure causing the rocks to form this network of fractures and have migration pathways following along those. All right, now with that, this is a fairly long lecture, and it's one of the benefits of actually doing something in an online mode like this is that I can basically talk all night long. I can have a 5-hour lecture if I wanted to, and you guys get to watch the whole thing. You can't do that in a lecture where you're restricted to 50 minutes. So with the help of this online lecture, it looks like I have caught up with all the material I wanted to get you to at this point. I will be back in class on Wednesday, at which point we'll start talking about I guess things that are certainly more relevant to anybody who's going to be planning a career in petroleum geology, talking about reservoirs, trapping mechanisms, and porosity. In Thursday's lab, it's going to be a busy lab because what we're going to do is we're going to combine 2 labs into one. As you know, the previous lab, Connor's, and you know he loves you guys so much that he just could not say goodbye. He wanted you for one more lab activity. So he dragged us out to his well field, played around with a resistivity meter, or a resistance meter I should say, and we're going to play around with some of those numbers in Thursday's lab. So it'll be kind of like a take-home exercise. I also want to give you some numbers that I was going to give you in the preliminary lab last week, so you get 2 number crunching exercises. There's another thing I want to do in Thursday's lab. I want to give you an opportunity to actually start seeing some physical properties that are important in petroleum geology, specifically porosity. There's different types of porosity that I would like you to have some fundamental understanding. So for that part of the lab, we're actually going to be looking at microscopes, or using microscopes to look at thin sections, bring back a little bit of fond memories from either sedimentology or from mineralogy, where you can this time start looking at pore space and try to get an idea of just how important porosity is as a variable in terms of fluid dynamics below the surface of the Earth. So all in all, should be a fun, exciting day. I will see you on Thursday. In the meantime, have fun and be prepared. I think when I come back from my little holiday on Monday, I might actually test you to make sure that you guys have been paying attention to what this lecture is all about. So expect a quiz Wednesday morning, and this will be the only time I tell you about it. So if you're watching this video, you know what to expect. It'll be a short multiple choice question type of thing, fill in the blank type quiz based upon the concepts of today's lecture. So if you haven't been paying attention, I would recommend you go back and maybe start looking over some things. Be prepared to identify and define some terms, etc. Anyway, have a good day.